Hello and welcome back to CERN. This is the Atlas experiment. Over the past 20 years we've been constructing it. Now the 3,000 physicists' thoughts turn to physics. How are we going to make new discoveries? Let's talk to my colleague Dave and find out. Recently, I guess the focus has been on preparations for the upcoming high-energy collisions.
There's really two aspects, two really core issues that we're dealing with at the moment. There's the preparation for the next run and the high-energy collisions, but there's also the analysing of the data that we took before Christmas in the short run at the end of 2009.
And what do you do with that data?
The collision data from the experiment is taken off the experiment, is read out from the experiment.
Mm-hmm.
We then analyse that data by distributing it around the world, and people are looking at the data in all of the different institutes around the world. It's another place where the global collaboration is really important.
Mm-hmm. I happened to see, before we broke for Christmas break, some presentations that were made that showed some particles. These particles were found in the data. What was everybody looking at?
One of the things we were able to see in this data is we were able to see the signals of particles which don't live very long. Mm-hmm. So they travel just a short distance in the detector and then decay. The interest of the particles which decay, as we go to higher energies, we're looking for particles, new particles that decay.
So you're going to see high energy particles because they're coming from particles you've created with a bigger mass?
Basically through E equals mc squared, the equivalence of energy and mass, we can produce more massive particles, so heavier particles can be produced in the collisions this year than were accessible in the collisions that we took last year. And that gives us extra reach for, or the sensitivity to possible new particles. So
previous experiments on previous accelerators have already measured a whole range of lighter particles. Atlas, just this past year, also measured some of those particles. But now we're going to go to a higher energy than we've ever used before to create more massive particles than we've ever seen before. That's where there'll be discovery. So when you turn on, when we go up to energy, it's not going to be the next day that you guys will make an announcement and say we found the Higgs?
Certainly not. It will take, it could take years to find the Higgs. I mean, I should stress, this is an experiment that we're in for the long haul. It's been an experiment we've been building for 10, 20 years, and it's an experiment we will operate for 10 or 20 years. And the science program is therefore a 20 to 40 year science program. Nonetheless, you say we turn on, maybe are we going to announce anything quickly? There are other things that might be there in the data that we might be able to see rather fast. There are new things, new exciting physics models which are just beyond the limits of the Tevatron, so the Tevatron wouldn't have seen them, but nonetheless that we might see at the LHC, that we could see within, not days, but we could see within months of starting operation in 2010. So the examples of this is the so-called theory of supersymmetry, where we would be looking for the signature of particles that might explain the dark matter in the universe, which is one of the big problems in astronomy at the moment, is what is this dark matter?
So there's some physicists, some theorists who've come up with a model which gives you particles that
That's right.
you wouldn't see.
Theory called supersymmetry, which actually gives you a huge number of new particles. It gives you a partner to every particle that we've already seen, but they would have to be a lot more massive. So there'd be things that they clearly would be things that we haven't seen in the laboratory so far. But one of those particles, the lightest of those particles, it turns out can be a candidate for dark matter. And so that might be the dark matter particle. We don't know, it's a theory, we have to test it.
So, and that we could get pretty early then?
That could happen quite early, yes. If nature has been kind to us and put the physics in just the right place.
Nature's been pretty tough with the Higgs, though.
Nature's been tough with the Higgs. Nature's also been a bit tough with supersymmetry as well, because at previous colliders, like the Large Electron Positron Collider LEP and the Tevatron, again, we've thought maybe we could see supersymmetry, but nothing has shown up. So we don't know. It may be there, it may not.
What if we don't see anything?
That would also be great. That would be really interesting, because we know that the theories we have, the theories of particle physics, which seem to describe all of the interactions very well at the moment, we know that those are going to break down at some point at some energy scale, and we know reasonably well what that point is. And it's something which is just about accessible with the LHC. So something, we're going to find something. We may not find the Higgs very quickly, we may not find the Higgs at all, it might be something else. But if it's something else, our standard model of particle physics is wrong, is broken.
And that's good news.
That's good news, because science proceeds by breaking things.
So in the coming years, we could find supersymmetry. With a bit more time, we might find the Higgs, and with a bit of luck, it could be we'll see something that we've never predicted at all. Regardless, it's going to be exciting.